Suppose I take some block and I lift it up to some new height. In which case there are going to be multiple forces that are acting on that block, but in particular I want to think about the force of gravity and then the work done by gravity in this case. So we know that the weight of this block is going to be downward, and if I lift it, then I have to apply some sort of lifting force, but I can also just concentrate right now on the weight here. So if I wanted to figure out how much work was done by gravity, I would have to take the force of gravity, mg, times the displacement, in this case, the height change here, and then I need to take cosine of the angle between the force vector and the displacement. So if I lifted this thing up, then the displacement vector is pointing up and the weight of gravity is down, so there's actually an angle of 180 degrees. So everything I'm using here is just from the work equation, where work is force times distance with that dot product. So in this case, because cosine of 180 degrees is -1, the work done by gravity lifting this thing up is negative mgh. On the other hand, of course, I could imagine if this block were just sitting here at that high height, distance h above the ground, and I dropped it, how much work would gravity have done then? Well, in that case, the force and the displacement would be both pointing in the same direction, and the work done by gravity would be mgh positive, and we'd expect the thing to speed up. So instead of treating gravity as work, we're going to give it a more interesting interpretation. We're going to want to introduce something called the potential energy, or I'll use the symbol PE for here. Different books will use many different symbols, but I'll just use these initials for now. And basically, potential energy is if you have some sort of force acting on an object, and all that matters is basically where you started and where you ended will change how much kinetic energy there is, how the speed is going to change. Then we can talk about energy, in a sense, stored in something like this. So we can basically understand this as the stored energy in some body. And stored because it has the potential to become kinetic energy. It has the potential of being the energy of a body's motion. So the only reason potential energies exist is because of forces involved. So there could be multiple sources of potential energy. We could have potential energy in a spring, and it can be shown that springs will have a certain amount of potential energy, that it will be 1/2 k. K is the spring constant. It's basically how much force the spring will give back when you compress it, multiplied by x squared. X is the amount you have compressed or stretched the spring from its equilibrium point. So squish a spring a centimeter, that's going to then store some amount of energy in the spring. The more you compress it, the more energy there is. The more you stretch the spring, the more energy there is. Kind of what you would expect. There will also be potential energies for electrostatic forces. There will be potential energies for all sorts of other forces involved, but we want to concentrate on, for now, the potential energy from gravity. So we saw that there's some amount of work that would be done by gravity if we were just to drop an object and it falls a height h. So we can talk about basically how much energy is stored in there as simply the weight of that body and how high up it is. So that seems nice and straightforward. But you might ask the question, well, height h, height above what? So for example, imagine I have these two different blocks, and they're both at the same level as each other. And I want to ask, well, how much potential energy do they have? Knowing their weight is straightforward. I know that what their mass is. We're doing this on Earth, so they both have the same acceleration of 9.8 meters per second squared. But then the height part of it. Well, for example, I could have this table here, and I could say, well, maybe the top of this table we could call height 0. Or I could call the floor height 0. In fact, why not just call the height these things start at as 0? It's actually completely arbitrary where you want to call the 0 point. That's going to be the interesting thing. So, while clearly, of course, the distance between the table here and the ground is going to be different, so let's call this, say, height 1 and height 2. Wherever we want to call our 0 position is still going to tell us something about how the potential energy will change. So just to give that a bit of concreteness, let's just say for now, with this first block, that 0 height is the top of this table. So this will be height 0. It starts at height h1 then. And let's then take a look and see then how much potential change there is when this thing is dropped. So initially, the potential energy is going to be mgh1. The final potential energy will be 0 when it reaches the table. That'll be height 0. And so the change in potential energy will be negative mgh1. Okay. Now, we could also then look and say, well, what if instead we wanted to say the bottom, that the height 0 is actually the ground level? Well, let's do that then. So let's change it so 0 is now down here. Now, what's the potential energy of this block? Well, it has a potential energy now of mgh2, and when it reaches the height of the table, the final height, we just have to basically plug in the height now in our new coordinate system. And so it'll be a distance of h2 minus h1 right here. So it's fallen a distance h1, so the new height is h2 minus h1. So again, if we do the change in potential energy, we're going to get mg, then we're going to have h2 minus h1 minus h2, so it's going to work out still to be negative h1. So even though I chose a different coordinate system, the change in potential energy was the same when the block falls that height distance. And of course I could get the exact same results if I said the level the block started at was height 0 and then it's falling down. No matter what I choose, as long as I'm being consistent with using my coordinate system, what I say is height 0 is arbitrary. Now that might sound a bit odd as well, because now it seems like I'm saying the potential energy is arbitrary. I mean, after all, in these two cases, one, I said this has how much potential energy there is. Here's another value. I use different h's. h2 is going to have a larger value than h1, so did I just say it had more potential energy? Well, with my choice of coordinate system, yes, I did. But again, all that really matters isn't potential energy, it is the change in potential energy. Now, we can't have the same arbitrariness with kinetic energy since it so directly is related to how fast something is moving and how massive the body is. But how much potential energy there is, we can be arbitrary. In fact, the coordinate systems we chose here are also a bit arbitrary because ultimately what's going to be the cause of potential energy, in this case with gravity? Well, the mutual attraction between the body and the Earth. So if I'm really thinking about gravitational potential energy, shouldn't I instead be considering the distance between the center of the Earth and the block itself? Ultimately, we know that's the direction that the force of gravity is pulling, towards the center of the Earth. Still though, even if I want to do that, I could then say that position 0 is the center of the Earth, and so in that case, we'll say we have the Earth has a radius r, sub e, that's the radius of the Earth, and we're starting with, say, some height h above the ground. So for simplicity then we could say that the potential energy initially is going to be mg and then how far away the block starts from the center of the Earth, height above the ground plus the radius of the Earth. Final potential energy is going to be mg then the radius of the Earth. And so again, the change in potential energy, just the two of those subtracting, and we still get negative mgh. So we do see just how arbitrary this ultimately is. We still get the same change of potential energy no matter what. If we were doing, say, planetary orbits, then it might matter how much potential energy we have stored in. But if we're just talking about figuring out how much the potential energy changes to see how much kinetic energy change there is, it is quite arbitrary what we call our initial starting positions. Now, here's something else that's quite nice about using potential energy here. We know that, and we're going to discuss more with the concept of conservation of energy, that all the potential energy at this block is going to become kinetic energy as it falls. But we saw that the change in potential energy only cared about height. Now, why was that? Now, remember that the work done by gravity is mg displacement h cosine theta, and theta is the angle between the force vector and the displacement. And so in this case, it was either, straight up or straight down we had. But even if, for example, we are on some incline, such as we have here, we are still going to ultimately have a displacement along the vertical direction. From our work equation, the only component of the displacement that actually will have work done on it is the vertical component. So we actually now have this really nice feature that the only thing that matters is not the angle of this incline at all, just how much the height changes. Whether we go over a very long slope or a very short slope, it doesn't matter because we still had that same height change. And it's only that height change that actually affects the change in potential energy. So for example, if I wanted to figure out how much kinetic energy change there was, how that's related to the potential energy change, the kinetic energy change here will be exactly the same so long as this is a nice frictionless system, so there's no other forces doing work on the body. We now have a new way then of figuring out, okay, a block slides down, it's accelerating. I could try to figure out what the acceleration of this block is as it goes down. I know if it were just falling straight down, its acceleration would be 9.8 meters per second squared. Going down this incline, it's going to have some acceleration that will be some fraction of that. And I could figure out what that acceleration is, and then over what distance that goes, and then figure out, okay, then how fast must it be going when it reaches the bottom, etc. That's a lot of work then. I have to do a lot of components, or I could just say, oh, I start from this height, I end down here, I know my change in potential energy, I instantly then can say how much the kinetic energy changed. If it starts from rest and then I know the mass, I can easily figure out, bam, right then and there, how fast it must be moving at the bottom.